what I'm going to do, since I didn't see many equations in the previous slides, it's okay. There is a lot of equations. So, okay. So first of all, I want to introduce basically what is the univariate theory of connection, and then we will see the bivariate and the multivariate. And what is the theory of connection can be classified in a mathematical way as a functional interpolation. Okay, what is a functional interpolation? So I will show this by a very simple, almost trivial example. Suppose that you have a point on a plane. Okay, everybody we know how to write all the line passing through these points. This means that you select a class of function, for instance, the lines, non-monomial, that pass through these points. So what the theory of connection wants to do is to write down all possible functions passing through the points. And by all function means continuous. Oops. It means continuous. Yeah, continuous, discontinuous, periodic, singular, even the Dirac function. Okay, or a function that are partially defined in some region and others. And so, how to do this? In this case, it's very simple, because basically your function is provided in terms of a new function. That's the functional interpolation. And in this case, it doesn't matter which one function you choose. All these represent all possible functions passing through these points, except the functions that are not defined at x1. Okay, but it makes sense because the function must be passed through that point. So because if it's not defined here, then you have infinite minus infinite, and it doesn't matter. So how to build this function, this constraint expression, this interpolation? This is built using this formalism here. So this is an expression that provides you all possible functions satisfying any constraint. And this is built up by using the free function. This function must be completely free. Okay? And these are some set of n assigned linearly independent functions. Okay? So you can choose monomial, Fourier, whatever you want, a combination, whatever you want. And these eta k are some constant, some coefficient that are coefficient function. For instance, you suppose that you want to find out all possible functions where you know the second derivative at -1, you know the function at 0 is assigned, at 2 is assigned, but at 2 you know also the derivative. So you apply this formalism for each one of these constraints, and you derive the expression of eta in an analytical way, and you find out this expression, and this expression represents all possible functions that satisfy all 4 constraints simultaneously. So this is an example on how to use this to describe trajectory in 3-dimensional. So suppose you have a set of endpoints described by these vectors here. So these are the 3 projections. These are the 5 points. So you have the G vector is a vector of a completely free function. It doesn't matter which function you are using. What you obtain is a trajectory that is passed through these points. And how to use this, for instance, to solve differential equation? Suppose that you have a second-order differential equation with a non-constant coefficient, non-homogeneous, a typical boundary value problem. So the boundary value problem is your constraints. So with the theory of connection, you can derive an expression that always satisfies this constraint. So by substituting this expression, okay, in the original differential equation, you obtain a new differential equation, a little bit more complicated in terms of your free function. And this is a unique, actually a new mathematical objective that has not been analyzed, fully analyzed yet, because this is a second order differential equation, but this differential equation has no constant of integration. There is a unique solution of this differential equation. There is a unique function g that satisfies this differential equation because the constraints through this expression are embedded into the differential equations. And so any solution of this differential equation basically provided the optimal g that satisfies this equation, that satisfies your differential equation. So since g is a free function, you can express g as a linear combination of any set of linear independent functions, the derivative and so on. And so if your differential equation is linear, then what you obtain is an expression that is linear in your unknown psi function. You can compute at this point the psi coefficient, okay, by least squares. This is basically a flow chart explaining how to solve. So you have a given differential equation, is subject to n constraints. The theory of connection using a set of n linearly independent functions that you choose derive your coefficient function eta k. So at this point you have the constraint expression. This always satisfies the constraint. You substitute in and you obtain a new differential equation, and then you discretize and you obtain the solution by least squares. Okay, so no more integration by step. You solve the entire differential equation simultaneously. And you solve the same way if it is an initial value problem, if it's a boundary value problem, or a multi-value problem. So this is an example. For instance, you have a third order differential equation. I use this expression because I know exactly the analytical solution. And these are the constraints are three constraints where you know the function at 1 at pi, but you know the derivative of pi divided 2, basically. And I compare the solution with basically the state of the art of a differential equation, which is Cheb-Fan. Is a toolbox that is free and is maintained by mathematicians. It contains, you know, like a spectral method with collocation point and various different kind of things. And we experience basically 8 order of accuracy gain in the solution and 2 order of accuracy gain in the speed. So we obtain basically a machine error level, okay, of precision. To show how powerful is this approach, I use the same third order differential equation, but at this point I introduce an absolute constraint, a relative constraint, that is, I don't know the value of y at minus or plus pi, and, but they must be equal, and an integral constraint. And so I apply this to the technique, and the Cheb-Fan is not able to solve this problem. So now, as you well know, when you have a differential equation and the solution is highly oscillating, you know, expressing the function in terms of a linear combination of a polynomial, like an orthogonal polynomial or whatever, is not a good idea because you need a lot and you start to have numerical problem. And so I try to take advantage from the fact that we can reach machine error accuracy in order to keep limited the number of basis functions that you use. So basically the idea is to split the time in a chunk of time where you have an initial value problem. You integrate this by a very simple integrator like Euler simple, improved Euler, in order to obtain a sort of description of your solution. So now I can perform the least squares of your solution, and I have an initial guess of my unknown coefficient. And I start an iterative procedure, iterative least squares, to obtain the final value of the coefficient that guarantee me that the final value of my differential equation is accurate as a machine error. And then I use this as the initial value for the next. So I test this with a simple oscillator and an amazing result. And so I try to stress this method a little bit further. And I decided to apply to a chaotic system, a damping oscillator. And basically, this is a nonlinear differential equation. You need to use nonlinear least squares, but with only 2 iterations, I integrate in 10,000 chunks. Obviously, you lose some accuracy as you increase. In 10,000 chunks of 4 seconds, 4 seconds is typical to have a couple of oscillations, and I use only 100 basis functions. And at the last point, I have an accuracy better than 10 to the minus 12 on a chaotic system. Then, inspired by optimal control problem, especially the indirect method where you apply, where basically you have a state and co-state, and they are connected through the component constraint, no? So I decided to apply basically this technique to differential equation subject to component constraint. And so I choose this differential equation, and here I use a quite complicated constraint. For instance, a relative constraint in zeta, the derivative of y linked to x, and x, y, and the integral in zeta forming a new constraint. So it's very complicated. These are linear constraints anyway. And what I obtain is basically machine error solution with only 27 basis functions with a beautiful condition number, 30, which means that the technique is very robust. And this is basically the summary of just the application to differential equations. So, first of all, it provides an approximate analytical solution. So, since this is an analytical solution, then this is useful for subsequent manipulation, and so for to perform derivative or integral of your solution. It unifies the way the initial value problem, boundary value problem, or multi-value problem are solved. The robustness is very low condition number. Speed is an order of milliseconds, good for real-time application. Recently we published on Astronautica with Professor Fulfaro, optimal landing, optimal intersect, using this technique. And the accuracy is a machine error level, and constraint you can take care of many different kinds of constraints. By the way, we are working on inequality. We have a beautiful result in inequality, also in infinite constraint. So now we move to the B variant. And so our G function becomes a G of x and y. And so if you have now the constraints become function. So if you have a constraint that is a function definition in only one axis, in this case only defined in x, you have a sinusoidal here, then you have a linear function, then you have a sort of a Gaussian function here, and another linear function. Then the theory as derived from the univariate can be applied also to bivariate. So this is, for instance, the solution you obtain if you choose the free vector g as the free function, which is a g of x and y equal to 0. So it's the most simple surface that you can choose whatever you want here. You can choose even using a modular arithmetic or this is an example of this. So I have I define basically two constraints, two functions. One is a sine of a 7x, so it's this oscillating red, and the other uses modular arithmetic, so it's discontinuous. And here you see that you obtain a surface that from continuous becomes discontinuous. Now, this is the most important slides of all the presentation. This is the way that the theory of connection has been devised for one dimension. Okay? So suppose that you want to derive an expression that always satisfies the derivative of x1 and the derivative of x2. You obtain with the theory of connection this expression here. Now here you collect in one side all the terms that do not include your g function. And the other side all the terms that include your g function. So these two quantities here, they have a very specific meaning. So this one is one interpolation function. It doesn't matter which one, but is any function that satisfy these two constraints. And this other part here is all possible functions that is a 0 at your constraint, that are unperturbing your constraint. And so, at this point, you can build, you can extend the function to n dimension. So if you have the capability to find an interpolation function in n dimension, then you are able to write down all possible manifold that is described in n dimensions. So now the problem is how to derive an interpolating function in 2 dimensions. And this has been done by Professor Kunz at MIT, who devised basically the Kunz surface. So if you have in a domain 0, 1, 0, 1, you have a boundary function at 0, at 1 in x, and a boundary function at 0 and 1 in y. Professor Kuhn proved that this function, the function you obtain in this way, is a function that always satisfies this constraint. Okay, is a unique function that always satisfies this constraint. So using the solution of Kunz, we can extend this theory to all possible functions that satisfy this constraint, just by adding basically the 3 terms that are always 0 at the constraint. This is an example. This is the Kuhn function. So we have these 4 constraints here. So these are representing the constraint function at the edge. So if you choose a g of x and y equal to 0, you obtain exactly the Kuhn surface. Now if you choose any kind of random function in x and y, you obtain a function that is whatever it is, but it satisfies always your constraint. It's possible to extend the theory to multiple constraints, Here you have 5 constraints in X and 3 constraints in Y, and this is what you obtain with the G of X and Y. And this is what you will obtain if you use a G of X, Y, the free function, that is modular arithmetic in both sides, so is discontinuous in both directions. You don't need to do this if you don't need it, but just to see, okay. So it's possible also to extend because we start recently to attack PDEs, basically to extend the theory to solve not only a function at the edge, but also the derivative, so Dirichlet and Neumann constraint. And the Kuhn expression can be easily generalized in this way, where you have a function, its derivative at 0, the function and its derivative at 1, and the similar. Your W vector in X and Y are a little bit more complicated, and you can express all possible surface satisfy this boundary constraint. So now the step is going to the n dimensions. And so your G of X becomes a G of X bold, where it is a vector of n dimension. And there is a paper recently we published in mathematics where there is a mathematical proof that the generalization of this is provided by a tensor form with a matrix tensor here that represent one interpolation function, and then you add all the possible functions using the same identical formulas that are 0 at the boundary. In this case, this vector here, where each index indicate a variable, the first variable, second variable, and so on, but can be expressed in this way. So where you are free to choose a set of function hi. In this case, the variable k is subject to LK constraint, okay? And this constraint must be expressed as a function or derivative, second, third derivative, it doesn't matter. Now, these coefficients here basically are simply obtained by inverting the matrix, okay? And this is basically the generalization. We start to apply to very simple PDEs, where in this case we have just Dirichlet condition, and we obtain machine error accuracy using least squares. And example of application are many, because in solving differential equation is basically the first applications we have. Integral differential equation, we already solved this. Here is for electrical circuits, and it doesn't represent any complication. So it can be solved by the same things. Calculus of variation, I present a paper with one application of this, because at the very end, calculus of variation is a minimization of an integral that contain a function subject to constraint. So the solution of this, the extreme of this, is represented by the Euler-Lagrange equation. Well, it's not, it's a necessary condition, is not sufficient, and you can solve this also by the same identical technique. And recently, and I will present in Portland, how to apply this for analytical linear optimization. It is quadratic programming and nonlinear programming. We have a closed form solution for quadratic programming and beautiful solution for nonlinear programming. That is still working. Engineering, there is many applications everywhere, in astrophysics, in visualization. And so this is basically the conclusion of my talk. So I presented a technique that is a functional interpolation,
basically it's called theory of connection. It can, or it can, it can take care about absolute constraint, relative constraint, linear constraint, integral constraints, and infinite inequality. I already showed some example in the other papers. So I presented the multivariate constraints, and I will start to apply also to orbit propagation, real-time optimal control, landing, docking, Lambert solver, analytical optimization, and all. We want to try to attack the finite element and try to embed in the machine learning, the capability of taking care of the constraints. If you are interested in this, we publish different papers in mathematics here, joint computational mathematics, and just write me an email and I will send up to you a PDF. Thanks.